I'm going to move some of this stuff out of the way because you can't see what I'm talking about, but it's a taskbar that, oh, here comes Cormisha. Okay. Okay, it's a taskbar that is in my way, so I can't see what's happening. Okay. And Cormisha's here. Welcome, Cormisha. Okay. There's just 4 of us. I don't know what happened. I've been on waiting since 2:30, and y'all have been on, but we were on the same account, but we weren't seeing each other. So I finally, well, I saw that in the messages, and that's when I thought, well, let me log off and log back on again. And it was the same thing. I mean, I didn't change a thing. I logged off and then logged back on the same screen, and there Roy was anyway. And then later the rest of you came. Yeah, yeah, yeah. I don't remember when it was. I had you on there connecting to audio. I don't know, for it must have been shortly after, maybe 3:20, 3:30, something like that. So it wasn't long after that. I just sat here and watched you. I said, well, at least one person and I are on the same page, but I couldn't get you in. Um, so that's when I decided to go back and check the messages, and sure enough, that's when I saw all the rest of the stuff happening. Well, maybe it worked out for the best. I hate to say that, but because I didn't have a chance to finish typing up all the lab, so it looks like we're probably not going to get to lab today anyway. So we'll just finish this chapter and maybe start on the next one. I think we're ahead of schedule anyway. It's the only class I'm teaching this term that seems to be ahead of schedule. So y'all have been doing really, really well. Now at least we're covering ahead of schedule. I've got an awful lot of people who haven't turned in anything, and a lot of issues that I don't have anything back from. So I'm going to be going back and checking to make sure there's no messages out there that I've missed. It could be, I don't know. Are all of you up to date on all your tests and labs, or have you still got some out? Okay, that's good to hear. Okay, okay. I just want to make sure because I was missing some people. Some of you have just been so good about having things in just, I mean, almost immediately, and then things just slow down. Valerie has most of the stuff in, I think, like you said, maybe just a couple, but we have been hitting things hot and heavy for the last few weeks, so maybe it's a good time to put on the brakes a little bit. So anyway, let's go with the current slide. And this is where we left off last time. I think we just had started talking about this slide. Let me scoot Roy over. He's in the way here. Okay, got him. Okay. And I believe this is where we were. Is that your recollection as well? This is chapter 20, shaping the Earth's surface. And here we got to soils, which, as I said, is the most important part of the whole course. You know, I'm a soil scientist by training. Okay. What are soils? They're mixtures of unconsolidated, weathered earth materials. Okay, let's stop there. What does that mean? Unconsolidated means they're not solidified. It's not like rocks and minerals that are bound together somehow. This is the residue, you might say. This is the broken down pieces of the earth materials. Okay, so mixtures of unconsolidated, weathered. Now what does that mean? It's gone through these weathering processes that we were talking about in the first part of the chapter. Chemical weathering, physical weathering, or mechanical weathering, and biological weathering. It's gone through these things, and these are the materials left over, small materials, okay, left over. And humus. Now, what in the world is humus? I think we talked about this last time too. This is old plant material. Not plant material you can tell what it was anymore. It's altered. And it also is somewhat decay resistant. It's not totally, but it's somewhat decay resistant plant material. And what this basically comes down to be, and I think I asked this question last time, is what is it you think makes a rich soil? How would you describe it? And several of you have several things about it, which are very good things. But one of the things I was sort of expecting to hear and didn't quite hear, but then I kind of did, was dark. Usually if the soil is nice and dark looking, we think it's a rich soil. Okay? Well, that's not always the case, because that dark color is basically what humus is. It's actually a film that is leftover, altered plant material. It's sort of the part that doesn't decay away as rapidly, and it coats the soil particles, and it does some really, really good things for the soil. And it seems like this is about where we left last time. A humus mixed with a sandy soil. Now, what's wrong with the sandy soil? The water just flushes right through. Now, when you've been having rains as frequently as we have this spring and summer, that probably wouldn't matter. Plants can keep growing because they have rain just about every other day, or sometimes every day, or twice a day. But in most seasons, maybe you only have rain once a week or once every 2 weeks. On a sandy soil, the water just flows right through it, and in 2 weeks' time, the plants are starving for water. Okay? Well, what does humus do there? The black, decayed, altered plant material coats those sand particles, and now that holds the water, because humus is really, really good about holding water. Now, this is a strange way to say it, but it's how I think about it. It doesn't hold it too tightly, though. It keeps it from flowing through like it would through sand, but it hangs on to it, and then the plant root comes along and can suck the water away from the humus, and the humus gives it up really easily. Okay? So humus will make a sandy soil more water retentive, meaning plants will have water for a longer period of time. Okay? What does it do to a clay soil? Clay soils tend to pack together, and especially when they get wet, the water fills every pore space. Okay? And then the clays get really slick. I don't know if you've ever been on a clay road when after it's rained, you can slide all over that thing. You have to be very, very careful driving there. Okay? We have dirt roads in the part of Georgia where I live, and some of them are notorious for getting people in the ditch because they just are so slick. What does humus do to a clay? It sort of separates those clay particles so they don't slide past each other. And now, and the other thing clay does, it holds moisture really, really well. If you dig up a chunk of clay, even when it's been really, really dry for weeks on end, that clay, if it came from deep enough, is still pretty moist. But it sure won't let the plants get it, because the clay particles hold it more tightly than the plants can yank it away. Well, what the humus does is make the water more available to the plants. So humus, even though you think it's making soil richer, what it is doing is making the water more plant available. That's the main thing that humus does. It does have some mineral in it, because plant materials have minerals in it. Every leaf out there has magnesium in it. So it does have some mineral content, but that's not the major thing. It's not making the soil richer. It's making the soil a better source for water for plants. That's the main thing humus does. Okay. Now, going back up. Mixtures of unconsolidated weathered earth materials. What are those weathered earth materials? Well, now they say quartz sand. That's what most sand is quartz. Okay, I'll give them that. But sand is not associated with a mineral. We think of it as quartzy sand. We think of beach sand, that's white sand. That's quartz, mostly. Okay? But if you go to some beaches, I believe Texas would be one, the beaches are not beautiful white beaches like they are down on Gulf shores. They're sort of brownish or grayish or something like that. Even over in Mississippi and Louisiana, the beaches are not particularly attractive, okay? The Florida and Gulf Shores type beaches, they're beautiful. That's because they're mostly quartz sand. But you see, sand is a particle size. I think I gave you this before. If you think of two dimes together, the thickness of those two dimes, that's the maximum size of a sand particle. Anything bigger than that is considered gravel. Anything down to that and that you can still feel grittiness in, that's a sand particle. So anything that feels gritty when you rub it between your fingers, that's a sand. It doesn't have to do with the mineral content. If it's a piece of goethite, that is sand size, it's sand. Okay. Now, they left off silts. Silts are the particle size that's in between sands and clays. Granted, especially in the areas where we live, there aren't that many silt materials, okay? We either have clays or we have sands. But in some parts of the country, the silt makes up a good part of the soil. Not a major part, but a good part, okay? And what a silt is sort of the floury type texture, okay? They sometimes call it dust. If it feels like flour when you put it between your fingers, you can't feel any grittiness at all, and yet there are individual particles there, that's usually a silt. The clay minerals, that's the one when I said take that single dime and imagine slicing it into 1,000 slices. Two of those slices together would be the maximum size of a clay mineral. Whoa, that's small. And they get even smaller than that, less than one slice, okay? That's a clay mineral. Clay minerals are sub-microscopic in size. They've just they're materials, if you think back in the last chapter or two that we talked about them, they are where minerals have weathered away and then reformed these tiny little particles. Those are your clay minerals. Now they are really good about holding moisture, too good about holding moisture because they don't let the plants have any. The silts are a nice size to have mixed in there with your sands and clays because they tend to separate that. But like I said, we don't have that many silts here. Now, the other things they mentioned here, metal oxides. We already talked about this before with iron oxide. That's what coats the surface of those tiny little clay particles is iron oxide, and that's what makes the clay look red. The clay itself is really a dingy, whitish, grayish type color. It's not usually red. Those iron oxides on the surface of the clays, that's what gives them the red color. Okay, salts are just other materials like sodium chloride is the most common salt, but you have potassium chloride, calcium chloride, calcium nitrate, potassium nitrate. I mean, you just have all these salts that are, they can be mixed in with the particles. Okay, those are just things that are usually dissolved in water, and if the water evaporates away, they just get hanging around in the clay. All right, now the book mentions next a loam, and technically what a loam is, and this definition is not too bad, it's a soil containing varying amounts of sands, silts, and clay. So you have mixtures of all those together mixed with an abundance of humus. Now, that makes your very best soil, okay? Unfortunately, we don't have that many loams here. We have sandy clays or clay sands and things. We just don't have that much silt here, and we don't have that much humus here. And why is that? Because we have high temperatures and high moisture content. And between those two, your chemical weathering eats up that humus. The humus is somewhat decay resistant, but it's not totally resistant. We put pine straw on the hillside where our house is built, where we have a path going from the upper part of the yard to the lower part, and it doesn't just wash downhill. Some of it does for sure. It decomposes, and about every season we have to put another layer. Sometimes if we put a really thick layer, we might go 2 seasons, but we got to do it, otherwise the soil washes away. So that's what a loam is. It's a soil containing varying amounts of sand, silts, and clays mixed with an abundance of humus, plenty of humus, and they say it's also known as topsoil. Well, in some parts of the country that's true. Topsoil actually is the top layer of a soil. Okay, that's what topsoil means. It can be a sandy soil, it could be a clay soil, it could be any kind. Usually the heavier clays are deeper, but a good soil, the topsoil is going to be mostly a loam. Out in California, where they do some of the biggest agriculture in the nation, they are notorious for having these wonderful loamy soils, and that's why they can grow such great crops. But of course the problem out there, they have to irrigate everything, and that's one reason the soils are so good, is they haven't had all the nutrients washed out of them. Here where we have so much rainfall like we've had this year, and actually last year too, it will just wash the nutrients right out of the soil. I don't know if you remember in South Pacific, I'll wash that man right out of my hair. Well, the rains that we've been having just wash those minerals right out of the soil and leave us a pretty infertile topsoil, not a loam. Okay. Now, what is a subsoil? That's the layers underneath the topsoil. Subsoil, beneath the soil, topsoil. These are typically less fertile, okay, than the topsoil, because the topsoil is usually where most of the humus is. That's the main thing, and the humus holds the minerals. Clays hold minerals, but they don't release them easily. Humus holds minerals, and then they release it pretty easily to the plant roots. The sand particles don't hold minerals at all. Silt particles don't usually hold minerals well, but that's why the topsoil is more fertile, not because the humus is more fertile, because the humus will hold the mineral content better, the fertility better. Clays are very fertile too, but they are very slow at releasing that fertility. Now, the subsoil also can contain more rocks and sometimes more mineral accumulations, which could be good or bad. If the minerals are something the plants need, their roots will go down there and try to get it. But if those minerals are things that plants don't particularly need, then they could just salt up the roots, and they don't do. The main thing is the less humus. The humus stays in the topsoil. It's not living anymore. Okay. Now, out in the Midwest, or here in the Southeast, in some places we measure our topsoils in inches or fractions of inches sometimes. It's just terrible. Some places the subsoil is exposed on the surface, and it's almost like that's your topsoil, okay, because the soils have eroded away so badly. Out in the Midwest, however, they measure sometimes their topsoil in feet, not inches, okay? And they can come in with a bulldozer and move soil around and dig into it and stuff and still have plenty of topsoil left. Even if they moved off a foot or two of topsoil, they still have plenty of topsoil left. Those are wonderful soils. Now, why is that the case? We'll talk about that in a later chapter, but basically the glaciers that we'll talk about in a later chapter brought down those topsoils from Canada, and then when the glaciers stopped and started retreating, melting and retreating, they deposited those topsoils on our Midwest. And that's why our Midwestern soils are some of the richest, deepest, finest topsoil you'll ever find anywhere on the planet. Okay? Now, another thing about that in the Midwest, they have these prairie grasses that their root systems go way, way down because they got that wonderful soil to go down into, and it's sort of dry in the western part of the Midwest, so those roots are down there mining for moisture all the time. Well, guess what? Every year when a grass dies, its roots die too. So all the material, organic material, the humus that was roots now goes back into being humus. Okay, so that just is a wonderful cycle. Here in the southeast, our topsoils are so thin and the roots are so close to the surface. The roots do make their way down in the topsoil, but I have actually seen pictures of they have a clay layer here. The roots go down, bend, and go sideways, make a 90-degree turn because they cannot penetrate that subsoil. And that subsoil is not very deep. Okay, so at the little 2-bedroom bungalow we have over in Georgia, I put out 3 blackberry bushes. They were thornless blackberries, and they had not done very well here. They had not done very well up in Winston County, where I tried to put them there at my in-laws' lake house. So I took them to Georgia and put them on just solid clay, but we had just put layer on layer on layer of straw and pine straw on top of that, so we wouldn't be tracking clay in the house all the time. And those blackberries run their roots just in between the clay layer and the humus, and they just are sucking it up, and they have produced some of the best blackberries we've ever eaten. Those roots are right on the surface though, but they've had plenty of rain this year. So that's the one and only slide they have on soils. How sad. Okay. Now we move to, that was 20.3. 20.4 is called erosion. Now there is a little blurb right before 20.4, and that's called city weathering. And basically, in just about any city, they have, oh, here comes somebody, but I can't see who it is. Capri is here. Excellent, excellent. Okay. Oops, yeah, I'm putting it in the right place, I think. Yeah, Capri is here. Welcome for her, Capri. Oh, she's still connecting. Okay, she's in now. Okay, Capri, had you tried to get here earlier, or are you just getting here for the first time? None of us have been able to figure it out. I was on, y'all were on, but I couldn't see you, you couldn't see me. And finally, when I saw the messages going around, I went back and logged off and logged right back into the same place where I was, and there you were. Or there Roy was anyway, waiting to get in. And he had already almost given up on me. So, what's that? Well, basically, we just talked about soil, so you missed the most important part of the whole course. No, I'm just kidding. So you can go back and hear it on the YouTube video. The YouTube video won't be very long today because I didn't start the recording until about 23 minutes ago. So because nobody was here, y'all were somewhere else. I was somewhere else. I don't know. Zoom, I think, messed up. Okay. So we're right now getting ready to start on the erosion. This is chapter 20. This is section 20.4, and it's on page 510 in my book. If you have the smaller book, it's probably listed as 20-6. All right. What is erosion? Well, just about anything could erode, I guess, but mostly we're talking about soil erosion. Okay. Okay, because soils sustain life. They're the most important things of this whole process of shaping their surface. If it weren't for the soils, we wouldn't be here. Plants wouldn't be here. Animals wouldn't be here. We got to have those good old soils. Okay, you can tell I love them. Okay, erosion is the process that moves soils away from where they need to be. It's the mass movement of soil. And all but one type of erosion is caused directly by gravity. They say erosion is caused directly by gravity. One type is not. We'll get to that a little bit later. But the rest of them, all the rest, and the major ones, that one type is a minor one. The major ones are caused by gravity. Now, here are two major mass movements of soil. The first is called soil creep. Okay? Now what that means is A slow movement of soil down a steep slope. Slow movement down a steep slope. What moves it down? Gravity. Gravity pulls it downhill. Of course it does. Okay? And soil creep is that slow movement down a steep slope. Like I have said several times, our house is on a hillside, kinda, and one side of the yard really slopes down pretty drastically, and that's where I put terraces and planted azaleas and did everything I could to slow it down, but I had to leave a path so I could get a lawnmower from the upper part to the lower part and vice versa. I didn't want to have to build a shed down there and shed up here and have two lawnmowers. So I had to have a path in between, and that's the path where I have to keep putting pine straw just about every year just to keep, because if I don't, that soil goes right on down the hill. Creep is a slow movement. Soil creep is a slow movement. What a landslide is any slow to rapid movement, downhill movement of materials. And that you see more so in the western part of the country, and places where you have high mountains. In the mountains, sometimes a landslide is called an avalanche. Now, sometimes avalanche refers to snow, but an avalanche could refer to boulders and rocks and things like this. So landslide is any slow to rapid downhill movement of materials. The places that are notorious for that are some of the soils in California again. Those soils are so minimally weathered that they have a lot of what the clays there are what we call swelling clays. And like I said, out in California in the far west, it tends to be a bit drier than it is here. And those soils are great for dry environments. But when you have a lot of rainfall, especially sudden rainfall, those soils, those clay soils swell up, getting lots of water between the layers of the soil, and then they slide downhill. And the coast of California is very hilly too. And they have had, you can read about this and see about it if you go out and looking for it, some very expensive houses built on the hillside overlooking the ocean, gorgeous places, to build the houses in these areas, and then they get a sudden rainfall they not normally would have, and now the soils give way and those houses go sliding down with the soil. The landslide, they become house slides as well. And that's a really dreadful thing to happen if you've invested that much money in that location to have it. So here are some sort of, well, I can't get it to move. I've never seen this to this degree, but you can see it occasionally. If you see a tree, a stand of trees that's been there a long time, and down a steep slope, you can sometimes see trees that are done that. Now, you might say, well, the tree's just reaching for the sun. No, these trunks of the tree were at one time straight up, just like this one was. But when the soil went creeping down, it carried the tree with it, and then the tree kept trying to turn and grow upward toward the sun like it normally does. That's an example of soil creep. I've never seen one to this degree, but that's the example of it. You see, underneath here, you got solid rock. It's not going anywhere. Your soils form from the weathering of that rock, physical weathering, mechanical weathering, chemical weathering, biological weathering. The soils are forming there, but then on the steep hills, they get washed downhill. That's soil creep, okay? And you can tell by the way the trees get sort of distorted looking, they've been moved by that. The place that I talked about that my parents-in-law had up in Winston County, a lake place there, it's really steep, and some of those trees you can see a little bit of that bending toward, but never something to those degrees that you see down here. Okay, that's not saying they don't exist somewhere. I guess they do, probably out west where the soils are probably a little less stable than they are here. So that's an example of soil creep. Now that's just the first type of erosion, okay? Now, the major eroder is water, running water. And where does water run? Downhill. Everything moves downhill. Now, before we get too much in here, and by the way, the mass movement is sometimes called mass wasting. This book is the only place I've ever seen that, so if you ever hear that term, that's where it is. They have some examples here. What is the slope and percentage grade for the mountain road that drops 2 kilometers in elevation for every 1.2 kilometers distance in 3 kilometers? That's just playing around with numbers. I see nothing in there that is really going to affect anything that we're talking about here. They just acted like, well, we got to throw some examples in, so they did. Another place it says a class examined, this is 2.2 is not a bad, that has a good term in it, a gradient. A gradient is another name for a slope. Actually, a gradient is any change of one thing in regard to another. You can have concentration gradients, you can have pressure gradients, you can have temperature gradients, you can have anything that's changing over time or space. So that's not a bad question to do, but we haven't done anything that supports that question. Earlier in the book, yeah, probably so. 20.3, this is just about all that's on page 511. A class examined a graveyard to measure the displacement of tombstones by the process of creep. By measuring the tilt angle of the various tombstones, they determined the displacement to be shown in the table. And the date on the tombstones, the older the tombstones, the greater the displacement in general. Okay? Now they only show 5 here, and millimeters are pretty small, but this is still pretty significant. The more recent ones have been displaced less than the older ones. That's an example of creep. That's the same type deal as the trees that we saw in the last slide. And then they talk about some other ways to measure creep, soil creep. I'm not going to go follow up that too much. And then the concepts applied on page 512 or your 20-8, creeping trees. Okay, it says investigate how creep of soil has changed trees on a steep hillside. Now maybe you could go up, say, on some of the mountains like Double Oak Mountain or Red Mountain or somewhere like that, and see some trees that may be leaning especially on the steep sides of the hill. If you do, that's what they're talking about, the creep. So let's move to running water. This is on page 20-8. Okay. Running water is the most important of all the gravitational erosion processes. Why do we say gravitational? That's what's pulling the water downhill. Gravity is. Okay? And running water is the major eroder. Major eroder. Now there's 3 types of stream transport mechanisms. Okay? Now first thing that water does, it dissolves materials. Now we talked about this earlier when we were talking about hydration. Water is a great solvent, a fantastic solvent. So water actually dissolves material and carries that in solution down the hill. Now a lot of those materials that it's dissolving are your salts. Some of those are your good nutrient mineral salts. There goes your fertilizers down the hill. Okay. It could also be, remember when we had sedimentary materials and we had lithification process, that was compaction and cementation. Okay? Well, compaction we understand. Cementation was then what stuck the particles together and made it into a rock. Well, water can come along and dissolve those cementing agents, because remember the cementing agents were left after the water evaporated. If water comes back, it may redissolve them. So water does dissolve materials, and as it does, it then frees up materials to move downhill. Now, the other thing that happens, suspended materials in water. Now, the difference between a solution and a suspension. A solution is usually fairly clear, okay? It may not be colorless, but it should be something you can see through. I think of iced tea, or not iced tea, just tea, okay? It's a brown color, but you can still see through it. You can see your hand on the other side of the glass. It's a colored dissolved materials in there. Sugar water, that's perfectly clear. Salt water, perfectly clear. That's salt water at the beach. You can see through it, there's no problem, but salt is still in there, you can taste it, okay? But on the suspended materials, you can't see through them. Actually, one common one is milk. Now, this is not normally, not earth material, but milk, you can't see through milk. What milk is basically two things. One is calcium compounds suspended in the liquid, being water, that's milk. And that's one reason it's a white color. You can't see through it because calcium is usually a fairly white colored mineral. But you can also have fat particles suspended. I don't know if any of you ever lived on a farm where you may have milked your own cows. I doubt if any of you have. But when I was growing up, my earliest years, we always had a milk cow, and my mom went out every morning and every evening and had to milk old Roxy, okay? And she was a good milk producer too. Well, that milk had not been homogenized. The milk you buy in the store is homogenized. They spin it around so much, they suspend the fat particles so that it's completely distributed within the milk. Completely distributed. But just milk out of the cow is not that suspended. It is much bigger fat particles, and that cream rises. You've heard the term, the cream rises to the top. That's exactly what happens. You skim off the cream off the top and make butter with that. My mom used to do this all the time. She actually sold butter. And the milk that's left over is called skimmed milk. And most of the time in the store today, they just say skim milk. But that's where the name came from. They skimmed off the butter, the fat out of the milk, and mostly all of it went to the surface. And then you had skim milk or fat-free milk. Well, what they do today, they, goodness, what is that called? Centrifuge the milk. So when they do that, the cream, being lighter weight, goes to the middle, and the heavier weight material, the calcium materials, go to the edge, and then they suck off the cream that way because they've already homogenized the milk and made them so small. So suspended materials, water also carries suspended materials downstream. So when you see a stream, and the one in your book on page 512, you look down at that one, that's not clear water, is it? That's murky water. You look at a lot of water today that's run off, and you'll see it's very murky. That has suspended materials in them, okay? And those suspended materials make it cloudy, okay? Hard to see through. Now, the other thing, the other mechanism, it dissolves materials, it suspends materials and carries them off. Well, it also transports bigger objects like sand particles, gravel particles, even sometimes boulders that roll and bounce along the stream bed as they're being moved along by water. And again, gravity's doing the moving, but the steeper it is, the faster the water's moving. The faster the water moving, the more energy it has. The kinetic energy of anything is 1/2 the mass times the velocity squared. If you square the velocity, like you double the velocity, 4 times the energy. so it can move bigger pieces of material, rocks, gravel, even boulders sometimes. Now, stream beds do evolve over time. That should be on the next slide, okay, because that's, or a subsequent slide. Let's look and see what we have here. There's a picture of water going downhill, and I bet you when that rain first fell, that was very clear, beautiful water. Now it's pretty murky. I can almost guarantee you it dissolved some materials as it came down, but it also has quite a few suspended materials. That's why you have that murky look to it. Now, I can't tell that there's any rolling, bouncing, or sliding materials there, but if that water's moving fast enough and you put something down there to catch it, you'd probably find out it is carrying some materials in it that would be bigger than you thought would be possible for the water to carry. Okay, so that's what we mean. Suspended is all throughout the water. The other things are usually down at the bottom, just being moved along by the energy of the water. Okay, so running water, the most important gravitational erosion process. Okay, now, like I said before, that last slide or item down there, stream bed evolves over time. That should have been the next slide, and here's what they mean by that. And you're going to see this, and almost exactly the same concept show up later in the chapter. Here they talk about stream development. Later they'll be talking about landform development. They go hand in hand. But here they talk about water, movement of water. Stream development, if you have a landmass that's recently uplifted. Now what do we mean recently? Last week? Last year? Nah. We're talking geologically recent, as in the last few hundred years. Last millennia or so. The landmass was recently uplifted. Think the Rocky Mountains. They're still growing. The Tetons, still growing. Himalayans, still growing. Recently uplifted and still being uplifted. Well, there you have a steep gradient. There's that term gradient again. The change in elevation per change of this, horizontal. In other words, if you remember back to your math classes, slope, rise over run. If that's a steep slope over a small run, that's a large gradient, okay? A very narrow slope over a long run, that's a very gentle gradient. So we'll be talking about that. The youthful landscapes are steep gradients. Remember, early in the chapter, in the slideshow, the Yellowstone River, Upper River Falls, and how rapidly that water was racing down, how steep the banks were. That's because it was a recently uplifted landmass. How is recent? Hundreds or thousands of years, okay, not millions of years, okay. So you have to get the right terms here. Then they form these V-shaped valleys with hardly any floodplain. There's no place where the water sort of sits for very long. It just runs, and runs rapidly. Here you find boulders. Those are highly resistant rock that are resisting the movement of water. You have rapids as they're going over these boulders, and you have the waterfalls. The Upper Yellowstone Falls, that's very resistant rock under there, but it's still being eaten away. But the rock that was below it, it left a long time ago. So you have these waterfalls. Very steep gradients. A more mature stream bed, the stream gradient has smoothed and lowered some. It's not nearly as steep. The stream gradient is now much more gradual. And what happens here, the streams tend to meander over the floodplain. They find the places where you have the greatest drop and they go there. And then maybe they erode a little more and turn here. I want you sometime to get a map of the U.S. and find the Mississippi River. That's pretty easy to find. It's sort of right in the center of the eastern part of the U.S. And especially a map that shows great detail, and you'll see the Mississippi River does like this. I mean, it's meandering. Way up where it started, it flows pretty straight, but after a while, it meanders like crazy. And there are some places, and we'll see some of these coming up on the next slide. In fact, let's go on and get to it. Okay, there's your steep, youthful landscape on top. That's this one here. Notice how sharp and V-shaped the valleys are, how rapidly the water runs down. It's a very narrow river or stream coming down because the sides are really close together and they go quite rapidly. Okay, that's your youthful landscape. When you get a more mature landscape, notice these hills have worn down, or hills like them many millennia ago have worn down. They've eroded, and the soil has formed in the stream bed. Now the stream goes at a very gradual pace, much more slowly. No rushing downhill, just sort of meandering downhill. Okay, all the gradients have been reduced. And then in the old age landscapes, these are very low gradients. In fact, sometimes, I gotta wait till that moves out of the way, sometimes you have broad, gently sloping valleys, hardly any slope at all. Your water flow is really slow, sluggish, and you tend to have more floods here. And the reason is there is very little drop off in the land. So if you got much water, it fills the whole floodplain. Now, notice here, this is called a bow lake, okay? And what that indicates, as soon as we can get the picture back again, at one time this stream probably didn't follow the same path it's following now. Is this going to ever go away? There it goes. It probably came in and went here and followed here. But then over time, maybe something dug it out more here, it left there, and it left this lake here all by itself. That used to be part of the river. It's no longer. It's called a bow lake. For obvious reason, it's bowed. That turn that it made a different turn later. Okay? And you'll see those all along the Mississippi and other of the great rivers. Okay? Just go out and look at some of those. My wife's brother and his family live in Louisiana, in Alexandria, Louisiana, which is near the center of the state. But they have a camp house type place, a really nice house, over on the Cane River Lake. That's what it's called. It used to be part of the Cane River, a big, almost U-shaped lake, but the river decided to go somewhere else. This is fairly close to the Mississippi. It went a different route and left this lake sitting there, okay? And their place is on the Cane River Lake. No longer part of the river, but it once was, so it was Cane River Lake. Much more sluggish movement of water, and that's your stream development over time. Youthful, really rapid moving, narrow valleys, stuff like that. And a lot of erosion can happen there. As the erosion happens, though, it slows down the stream gradient because this erosion filled in here made this deeper here, and so there's less of a gradient there. Okay. Now, usually you have really good soils here, but also usually they're very prone to flooding. So it's a give and a take. Some of the richest soils in the U.S. are, have y'all ever heard of the Delta in Mississippi? They call a region of Mississippi, sort of central Mississippi, near the Mississippi River, the Delta region. And that's because it's really, really rich soil that has been deposited by the old river there for many, many years. And they can grow some great crops there, but it's very prone to flooding. And when they have years with lots of flooding, people get wiped out. Farmers get wiped out, they're left, and then people will come in and buy up the land cheap and do it until they get wiped out. So, pretty rugged place to make a living. All right. Here it is again. There's that upper river, Yellowstone Falls on the Yellowstone River. Look at that. That is a definite youthful landscape. Look how V-shaped the valleys are, all the way down, V-shaped. I mean, really V-shaped. How rapid, how great the gradient. Here the gradient is huge. I mean, going straight down almost. Here the gradient is still pretty great, and the water, you can tell, is just rushing down there. As it rushes, it has more kinetic energy. As it has more kinetic energy, it does more erosion. And that's what made these V-shaped valleys. Like I said before, this valley used to be almost flat across here, but the water has eaten its way down through the weakest part of that valley and continues to rush around and dig out more and more as it goes. It's exactly what dug out the Grand Canyon too. I've never been to it. My mom went to it once. She said it was just amazing. Everybody I've ever talked with that have been there just were amazed by it. My parents-in-law took each grandchild on whatever trip they wanted to go to in the U.S., and one of them got to go to to Grand Canyon. The whole family went to Yellowstone, but one of the grandkids got to go to, picked, Grand Canyon as their place they wanted to go. All of it done by water, carved out by water. Okay. Now the deltas. We talked about this earlier. This is now, and there were a couple of examples. I'm not going to focus on them too much, but each year a major river in a humid region transports about, and this is really worth a read, how much soil is carried off by these rapidly moving water sources. If you don't work the problems, read the problems. It's just amazing the amount of water that of soil erosion that occurs. Now, that same slide that you saw here, whoops, I went the wrong way. I went to the end. Sorry about that. Here, that stream development. That slide is on page 513 in the text, or 20-9. But just above that, where our slide showed this, they show a river valley that is much more an old landscape. And you see some of those bow lakes in there. You can see where the water used to run, and you see how the water just meanders around those low-lying areas. But if there's ever a flood, all of that is underneath water. Okay? Without flooding conditions, it's pretty good soil, I bet. But with flooding conditions, your whole crop gets destroyed. Okay? So that's that. I'm going to do a little bit of moving here because my book's not about to fall, but it's hard to read. I have a small desk here. Okay. Now, the term they used here, and I should have spent more time on it, floodplain. It's highlighted in your book, or bolded in your book. A floodplain is the wide level floor of a valley built up by a stream over times. It's called the floodplain because when the stream does flood, it goes all over that floodplain, just covers it. In a V-shaped valley like this, you have a flood, it's all down in the bottom. I mean, it really is eating away at soil. That's probably why these sides here are almost barren of plant life, because probably at one time there was a flood that came through and just wiped out all the plants on the lower part here. But most normal times the water is down here. But with a floodplain, where everything's really flat, the water goes everywhere. Okay, and that's why they call it a floodplain. Okay, and then this upper Yellowstone, the waterfall and rapids here, they don't tell us which one it is, but that definitely is a youthful landscape. Okay, then example 20.7, is talking about how fast must the water be moving, and you can read through that. But of course, it's talking about, I think, dealing with kinetic energy, which we haven't had. But it's still worth looking at those. And then they have what they call stream relationships. I didn't find that one all that useful. Now, here is where I'm getting a little confused in the book. Oh, here we go. All right. This is on page 514. They make it seem like a big topic here, which it really is. Okay? But in the text, it's one paragraph. Okay? But it's a very important paragraph. And this is the delta. Okay? Now, what a delta is, and I just was describing it earlier, deposits of sediments at or near the mouth of a river or stream. Deposits of sediments. Because you see, as the water comes downhill, it's bringing with it soil. The steeper the hill, the more it's bringing. Okay? It's bringing all kinds of material there. But then when it sort of flattens out, it can't carry as much because its energy is less. As the speed decreases, the energy decreases. So it starts dropping things out. And it drops the heavier stuff out first and keeps carrying the lighter stuff. Well, when it gets down near the mouth, where it's going to flow into the bay or the bigger river or the Gulf or the ocean or wherever it's going, usually there it's really tapered off a lot. And where that happens, the last of the materials that were suspended in the water, they tend to drop out. Those are the deposits of sediment near the mouth of the river or stream. Now, yes? Say that again? Spell it. Oh, gold. Okay. Okay, yeah. Now, actually, the gold, if I've never been around much water that had much gold in it, but the gold will actually come out usually not in the very lowest part because it's heavier, and it will usually be on, you're right, that will come out. If it's been carried from a higher place, it will come out as soon as it starts leveling off, but it won't be necessarily down in the delta. It usually drops out before it reaches the delta. But yes, you're right, and that's where they used to do their sluicing. Is that what they called it for gold? There was a gold rush. Yeah, yeah. There was actually a gold rush in Georgia in the 39s. You know, the 49ers were California. Georgia had one in the 39. It just petered out really, really quickly. But Dahlonega, Georgia was the major area, center point where they found that, and that's a very hilly area. And they had a big rush there. It petered out really quickly, and 10 years later, California had a really bigger one, and everybody moved out there then. After that, Alaska, the Yukon gold rush happened. I don't remember when that was, but no one had known much about Alaska before. Then they found gold up there, and all of them started heading up there. And again, they're in places where you have the downward flow, and what they do is sometimes you'll see this, the sluices slow down that downward movement. So a lot of what they're talking about here, the sluices wind around and make them do, so the gold comes out faster than it would before it would further down, because they sort of make their own deltas, you might say. So yeah, you're absolutely right. What's that again? Yes, exactly. Exactly. Because gold is very dense, and it will come out farther up the hill than way down at the deltas here. But the people who live in the deltas consider that deep white soil dark black gold. You know, they're pretty high on that too. So these deltas are deposits of sediments at the mouth of a river or stream, and the stream flow dissipates or slows as it's getting closer to the ocean, the lake, the bay, whatever it's getting to, and as it slows, more deposits come out. The erosive and sediment carrying ability is lost, and they start dropping it. Now, here's an actual picture. Here's a illustration of it. I wish we were in the classroom. I do that all the time. I know we can't be. But if we were, I would pull out a globe and show you Louisiana. Louisiana is right at the mouth of the Mississippi River. And Louisiana sticks out into the Gulf of Mexico. That's not two unrelated statements. The reason Louisiana sticks out, I would say, I'm just making a rough guess here, about a quarter to a third of the whole state of Louisiana is deltas that's been deposited that once was soil somewhere up in Canada or the upper Midwest that's been washed down, carried down the Mississippi River, and then deposited as it slowed its motion and dropped. And it's still going on. That's why some of those areas in New Orleans especially are actually below sea level. What happened there, they were anxious to build and stuff. They drained, they dug, they dredged the channel of the Mississippi deeper. They threw up some soil on either side. That created some of it. But the other thing is they got the water to moving faster through there. Well, then what had been deposited over centuries before now used to have lots of water in those soils, and now they subsided and collapsed and actually got to be below sea level. Well, people still built houses on them and stuff like that, and now when there's a flood, think Katrina, I mean, they got dumped, really dumped. And you can see that's happening here. Everything in sight here was probably one time part of the bay, the Gulf, the ocean, whatever it was. Just about everything you see here over time was deposited, and is still being deposited. Okay? There has to be some path for the water to get through here, but along that path you have the sediment. Okay? Now here's another way of looking at it. Down here is finally the bottom bedrock here. But on top of that bedrock, the river brought down water, soil, and as it slowed down, it dropped it out and sedimented it out. Now these are not horizontal layers necessarily, they're sort of curved because they were following the contour of the bedrock down here. And over time, at one time the beach was way back here. Now the beach is out here somewhere. All this in between is your delta, the sedimented materials that the river has deposited there over time. Okay. So fairly decent illustration, but if you were to be able to go and look at, I've never been to Lower Louisiana, but I've seen it on the map and read enough about it. That land there one time was up in Minnesota, Nebraska, Illinois, Indiana. It's all Ohio. I mean, all those big rivers came together and into the Mississippi, brought the soil with them, and as it was moving rapidly, carried that soil, but as it slowed down, dropped it out, just like the guys do when they're mining gold. You're absolutely right. So those are your deltas at the base, the mouths of streams or rivers where they dump into wherever, the ocean, the lake, the bay, the Gulf, wherever they're dumping. All right. Now the second major, and this is where we were getting to, second major movement of soil through gravity, and frankly it's still water, but now the water is not liquid water, it's solid water, glaciers. What glaciers are masses of ice on land that move under their own weight. they move because gravity is pulling them downhill. Okay? But here's the way they're way stronger than water, okay, in a sense, because they are so stinking thick. They form from snow accumulation over a number of years. How many years? Well, as little as 5 years. If you had 5 consecutive years of very heavy snowfall, that, in other words, not all of it melted from the previous year and it just piled on top of that, and then not all of that melted and it next year it piled again. In as few as 5 years, or sometimes as many as 3,500 years, 3,500 years, you built up these glaciers. Now, in those 3,500 years, you could have had some years where it built up and some where it reduced, but the buildup outdid the reduction. So you wound up with deeper and deeper of these glaciers. Well, the deeper they are, the heavier they are. And the heavier they are, the more they're pulled downhill. And that's exactly what's happening. Now, there's two names, two types of glaciers. One of them has two names. The Alpine glaciers, because they were first described and seen and studied in Europe, in the Alps. The Italian Alps, the German Alps, the Swiss Alps. The Alps cover several countries there, and these were very deep, narrow glaciers, and they were called alpine glaciers. Now we talk about any high region as being an alpine land and stuff, where it could be in Canada, it could be in Siberia or somewhere, but they still call it alpine. It has nothing to do with the Alps. Okay, but these form at very high elevation, where at high elevation the air is colder, the snow comes out and maybe never melts, or at least doesn't melt a lot, and they remain snow covered year round. Okay, forming at high elevations. They flow through the valleys, and because they flow through the valleys, they're called valley glaciers. That's actually the better name for them. Alpine means they're out of the Alps. No, they call all these valley glaciers means anything that's filling up a valley. And certainly the alpine glaciers are valley glaciers. But there's then these other kind of glaciers. They're called the continental glaciers. Okay? Now, I've actually seen what I'm classifying as one. I assume that it's what it is. When my wife's family, they used to take big trips about every 3 or 4 years. They, say, well, let's go do this, One year we went to Canada. I think we actually did it 2 years, separated by about 10 years apart. And we went to several, beautiful areas along Canada and drove for quite a ways, but we got out into, goodness, what is it called? British Columbia? Not British Columbia. Is that the name of the westernmost state in, I think that is it. Say again? Yeah, yeah, and out there was what they called I believe it was called the Columbian ice fields. Okay, uh, and it had to be a continental glacier. Now the sad news for that was when it had first been discovered by European type people. Of course, the natives there had known about it there for as long as they had been there. But when it was first discovered by Europeans, they were fascinated by it, and they marked where the tongue of the glacier was. Okay, the very end of the glacier. Melting water came out there. They put some sort of marker there. Okay, and that was only about 100, maybe 150 years ago, maybe a little longer than that. But to get from that point to where the tongue of the glacier is today, we had to walk a solid mile. The glacier had retreated that much over, may have been 200 years. I don't remember what the year was, but it wasn't all that long ago. It had been quite a while before they had discovered those ice fields. Okay. Oh, did you? Yeah. There are some places. Yeah. My wife was telling me she read something that someplace inside the Arctic Circle topped 100 degrees this summer one time. Oh my goodness. Did you go? Oh, okay. You're not a surfer. Okay, okay. I thought maybe you were. All right. Uh, yeah. Now, these continental glaciers cover large areas of a continent, and they say here in Greenland and Antarctica are the two most prominent and where the most of these are. But I believe, I'm almost certain that British Columbia and in western Canada, the Columbia ice fields, I'm pretty sure would be classified a continental glacier because they're really flat. They're not valley glaciers at all. Okay. Now, why are we talking about them when we're talking about erosion? Glaciers sort of just sit there, don't they? Oh, here's a pretty picture. We have another one in your book. Um, oh, your figure 2013 on page 516 or 20-12 shows a valley glacier. You can see the mountains on either side, um, and the glacier is basically filling the mountain. Now, this is at high elevations, maybe far north too. I don't know. It doesn't have to be. And rather than a river flowing down here, it's a glacier filling that valley. Not a river, a glacier. Okay? That is definitely a valley glacier. Some people would call it an alpine glacier. Not a continental glacier, which would hardly have any topography sticking up around it at all. Okay. Now, glaciers cause erosion. Three mechanisms. The first, the glacier, now you can't see it here. The figure in your book actually is a little bit better in showing it. The front edge of that glacier, there you can't see it because it's not in the shot here, but the front edge of the glacier, that's where the glacier is really, really deep, and there's a lot of weight, and that ice is going downhill, and the front edge of that acts like a bulldozer. So they call that bulldozing. Okay? It grinds up, picks up any loose materials. When I say loose materials, these can be boulders the size of an apartment building. Okay? And they carry these, push them along, because these things move awfully slowly, but they constantly are moving. So they push these things along. You don't ever see the motion, okay? But they are slowly pushing them downhill, and as they do, they pick up more and more and more. Well, at some point, most glaciers will stop and then start retreating. When they start retreating, that means they start melting. Well, that deposit they've been pushing along all that way, now sometimes if it makes for a pretty good dam, then it fills up a lake behind it. And those deposits formed there are called moraines, and quite often the lakes behind them are called moraine lakes. Okay? And we went to one when we were up there in Canada. I can't remember which area it was. It seems like it was in Alberta, called Moraine Lake. And you would not believe the size of the boulders that made up that, what I call a moraine dam, okay, that was sitting there, and the lake was all way up behind it, you know. Beautiful, beautiful lake up there. And we were downhill from it. All that water could have done, you know, if that hadn't been pretty strong. Now, there was water leaking through that moraine dam, but it was just basically being replenished all the time by whatever was upstream melting that time. So that's the first thing. Bulldozing materials ahead of it, those materials are called moraines. Now, another thing that's happening is The bottom of the glacier, picture this, the bottom of the glacier is moving along on top of soil somewhere the ice ends and the soil begins, and that the glacier may be, I mean, really thick above there, lots of weight there, and that glacier moving really slowly is grinding its way downhill, and that produces this powdery silt size rock flour. If you rub the stuff between your hands, it would feel like flour that you make biscuits or bread with, okay? It would not feel gritty at all. That's where your silts come from, predominantly from glacier. So that's why the Midwest and other areas like this, they'll have silty soils we won't have. The silts have all dissipated or disappeared before they got down here. I don't think any glacier made its way anywhere close to us here. So that's the process they called abrasion. That's basically, this is a weird way to think of it. Have you ever sanded furniture or sanded a floor or something like that? You put your weight on it and you push down and you take up the fine little layer that maybe is rough, and that's what you're getting rid of. That's what the glacier is doing to the soil underneath it, is sanding it off, okay, making very tiny little rock flour, silt-sized rock flour. That's abrasion. And then the third, and this sort of connects with abrasion some. Here's something weird about water. We've already talked about a lot of weird things about water. When you add pressure to ice, it melts. When you release the pressure, it refreezes. Okay? These glaciers have lots and lots and lots of pressure on them. They are so thick, so heavy, lots of pressure, that sometimes it is melting the water at the base of the glacier. But then, if temperature changes or the weight reduces a little bit, then it refreezes. Well, it may refreeze around rocks. So it plucks up rocks. I think of them as teeth, okay? And then these plucked up rocks pulls them along, and they really dig out. Whereas before it was just the weight of the ice in the glacier grinding down on the surface. Now you've got plucked rock, gravel, boulders sometimes, that are now being pulled along and just grinding into the underlying surface. That may have been rock. It's probably going to be soil before too long. Okay. Now, here are pictures of a fairly youthful landscape with V-shaped valleys, but then we had an ice age, and the glaciers came, and I'll have to wait till that window gets out of the way, and the glaciers, whereas here water flowed through these valleys, okay, going downhill, eroding as it could, but when the glaciers came and got really heavy, they dug out huge areas here, and that came out. So rather than a V-shaped valley, you have U-shaped valleys where the glaciers were. Okay, I gotta wait for it to dissipate again. Let's go up here. Whereas this was probably moving from a youthful to a mature landscape, some erosion has occurred there. The peaks were rounding up some, and the valleys were beginning to fill in, and that's why when the glaciers came, it was easy for them to dig them out again. But now you're left with horns here. What's left over is a glacier ate out this part and another glacier eating out this part. You're left with a horn. The arête, I think is how you say it, or arete, those are the sort of the crests there between the two glaciers. It was a rounded peak. Now it's a pointed peak because the glacier ate out on this side, this one ate out on that side. A cirque, I think is how you pronounce that. It could be just cirque, but I believe they pronounce it cirque. that is a rounded part that left a deeper part in here and maybe has a suspended lake up there. Okay, and they call these the rock basin lakes. Maybe the glacier ate its way through here, but then retreated, and then ate again and retreated, and it dug out deeper parts, and then when it finally retreated, it filled those parts with these rock basin lakes. Okay? Now, as soon as that gets out of the way, I'll show you one more feature, but it's all behind that. You can't see behind this rectangle, can you? Okay, here it goes. Here a fairly shallow glacier went where a deeper glacier went, and here you have a hanging valley. In other words, you get a waterfall there, okay, where one glacier stopped and went into the side of what was left by another glacier. Okay, so these are the three mechanisms of glacier erosion, and these are some of the features that glaciers leave behind in the landscape. Okay. Now, yeah, that's why I was waiting for it to go out so you could see it a little bit better. Now, if you think about that, you have heard the term the ice ages, right? I think there were at least 4 really big major ice ages, okay? Separated by so many thousands of years, you know. And in fact, Roy, I think you were talking about they think we're coming up on approaching another one, or we're yeah. Um, there are cycles in the Earth's weather patterns that these things happen and they retreat and happen. Well, these 4 major ones, when they were coming down, they were continental glaciers. I believe the whole nation of Canada was probably at one time, and maybe 4 times, underneath an enormous continental glacier. Okay? And it went tooling along incredibly slowly, pushing its way down, bulldozing in ahead of it, abrasing underneath it, plucking in other places, and as it hit softer rock, it dug in deeper. As it hit harder rock, then it met more resistance. So therefore, you had a lot of features. There's some people that feel like, I don't know if this is current thought or not, that the Great Lakes were dug out by some of those glaciers. That must have been softer rock there, and the glaciers really dug into them. Okay, and that's why you have those 5, I think it is, Great Lakes up there, just sitting in the middle of the country there. Actually, the border between U.S. and Canada almost. So these glaciers crawled along at very slow speeds, but they just kept getting deeper and deeper as it got colder and colder and colder. Crawled along and made their way into the U.S. Much of the northern plains were under these ice sheets, okay, and they kept coming down, but at some point, and I'm just guessing here, maybe around St. Louis or somewhere around there is about as far as they got, and then the climate changed and started warming again, and now the glaciers started melting and what they call retreating, and now they went back. Well, just like the deltas down at the river basin, where the glacier stopped and slowed down and then started retreating, everything it had picked up underneath, the plucking, the abrasion, and all like this, now it started depositing it. Some of it pushed ahead of it with bulldozing, others it carried along with it underneath. And lo and behold, that's why our Midwest basically is made up of Canadian topsoil, okay, ground down from Canada and deposited here, and then the glaciers went back up again. And they deposited more soil back in Canada as well. They have some really good lands there, but that's why our Midwest is just, I mean, you go to Illinois, Indiana, Iowa, Nebraska, those places, the soils are so deep and rich and wonderful there. They can grow some of the best crops in the nation. Their growing seasons are fairly short, so they can't do but one crop a year, but boy, do they ever have great crops then. As long as they can get the crops in time and out in time. That's the big problem there. Down here in the South, we don't usually have that worry at all. It's just that our soils are so thin and eroded that they don't produce very well, and highly, highly weathered. If you think about, we have year-round. In the wintertime, we have many days over 40 degrees, over 50 degrees. You have chemical weathering going on there. Anything above 40 degrees, you have chemical weathering. So year-round, we have chemical weathering. Up there, they get below freezing and stay below freezing, or at least below 40 and stay below freezing, below 40 just about all winter. So there's no chemical weathering in the wintertime. And their winters are quite long, not just 3 months, 4 months, 5 months, just like our winters are very short, 1 or 2 months sometimes it seems like, if that. Okay, so yeah, that's one reason you have such rich soils in the Midwest. The last type of erosion, and this is the less efficient than water or ice, is wind. And this is the one that, how can you say the wind is caused by gravity? It's not. So that earlier slide that said gravity is responsible for your weathering, your erosion, not wind erosion. Okay, not responsible at all for that. But the wind erosion is considerably less efficient than water or ice. The wind, even though it may go at high speeds, is still not got enough mass to have that much energy. Plenty of energy to do damage to houses and stuff like this, but not to transport very much mechanism, very much soil or other materials. Okay, but it does do some. Two major processes in wind erosion, and these are some of the same terms that you'll see in water and ice erosion. Abrasion. Okay, another name for that is natural sandblasting. Okay, have you ever watched some sandblast, say a building or something like that? They get high pressure air picking up sand, and they're trying to take off that outer surface that's dark and dingy and dirty looking, basically molded mildew, and get it down so you see the original limestone, the rock, whatever it is. That's what sandblasting is. Or it can be done with metals, getting rid of the paint, getting rid of the rust. You're eating away at the outer surface. Well, that's what wind does. It just doesn't do it at high enough velocity to be major, but it does do it. What comes out of that is called a vent effect. That's vent means wind, or air movement. So this is a feature, like an artifact is a feature that came out of whatever produced it. A vent effect is a feature that came out of wind. That's what's produced by wind. The shape can depend on the prevailing winds, and here's what we're talking about there. Here it seems like we get wind from just about every direction. Our prevailing winds are from the west, but we can get these northern winds coming in, we can get southern winds coming in, we can even get eastern winds coming in. So we don't have predominant, our westerly winds are predominant, but they're just mildly predominant. Okay, if you have ever been in San Francisco, or basically just about anywhere along the west coast, the wind always has come blowing off the Pacific Ocean because there's nothing there to stop it. Okay, it just blows across there and it carries across quite a ways. So if you have these prevailing winds that are constantly, it seems like from one direction, you will form, this rock at one time was fairly symmetrically shaped, but the wind constantly blowing here, carrying with it little particles of sand or other things that are blasting away, chipping away at this side of the rock. Now the rock has a definite slant to it. Now, if you were to get a change of your prevailing winds and they started coming from the other side, then you could start eating away and doing the same thing here. This doesn't happen much. Usually it's a prevailing wind from one direction. Okay? We just don't have usually as strong a wind at all unless it's associated with a tornado or a hurricane, and those winds can come from every direction because they're spinning, so we don't usually get many ventifacts around here. But if you go to certain areas in the west where you see those arches and other things like this, a lot of times they were caused by wind, maybe a combination of wind and water, but wind has caused the things that are really high up there. Water never got up there. That was a ventifact. Okay? The shape can depend on the prevailing winds. Now, I didn't notice that as much with the rock material because I wasn't really looking for it, but I had a couple times I had to go from the Bay Area in San Francisco up to Sacramento for one reason or another, and along that interstate that's between those two cities, they planted trees in the middle of the interstate. The trees all leaned like this because those prevailing westerly winds just kept them bent that way. That wasn't soil creep, that was wind. That was a ventifact on the trees. Okay, and it was just amazing to see all those trees leaning the same direction. Now, that's the first kind, abrasion, natural sandblasting. But the other is deflation, which is almost the same thing, it sounds like to me, but it's loose material picked up and carried away by the wind. Okay? Here's the difference. The abrasion is when it carries material and hits against the rock, breaking it. That's the abrasion part. Deflation is then when the wind comes along and picks up these broken pieces and carries them off. Okay? That would be the deflation. You have the same thing in erosion. They call this in raindrops. The first thing when the rain hits the soil, now I'm talking about soils now, big old heavy raindrop hits, and if that soil is exposed and doesn't have plant material on it or mulch or something else like on it, then the first big drops of rain hit, and it they have a name for it. I can't think of it right now. Detachment, that's it. It detaches the soil particles from the other soil particles. And then the second part is transport. When the water runs downhill, picks up those detached materials and takes them down. The same thing here. The abrasion is the detachment part. The deflation is the transport, carrying it away from the rock, blowing it on further. That exposes more to be abrased later. Okay. Now, these wind-blown deposits have names. Usually when they're down near the sea, they're called dunes, sand dunes. Now, the reason they're usually sandy is the sand drops out at lower speeds because it's heavier. The clays and the silts will be carried on out, kept on going. The dunes, though, if they're sand dunes, they've been deposited there. Low mounds or ridge of sand or other sediment. That's one type of a deposit. The finer dust that's deposited, and that's usually not in one area but over a large area, that's called loess. L-O-E-S-S. Pronounced luss. L-U-S-S is what it sounds like, but it's spelled L-O-E-S-S. Fine dust deposited over a large area. Have any of you been following the, I guess it's on weather or other things like this? There have been some really major sandstorms in the Saharan desert. And some of these sandstorms are bringing loess across the Atlantic Ocean, and that's making some of our sunsets and sunrises brilliantly red. Okay, that soil, those deposits, you can't say, oh, here's a pile of them. That would be a dune. No, these are lightweight, and they're just carried and dropped just about anywhere. Now, I mentioned sandstorm, and I think we've also mentioned things about things we've done to our country, okay? And what I'm referring to is when we were doing the western expansion from the East Coast, the original 13 colonies, and making our way slowly further west across the continental U.S., building America basically is what we're doing, building the USA. When they happened to be going through the Midwest, it just happened to be a time when there was lots of rainfall and very good growing conditions in that area of the country. Now, the people getting there, they hadn't been there before. They didn't realize this was unusual. They thought this is what they always had. And they said, my goodness, look at this rich soil. Look at all this rain they're getting. Why are they not growing crops like crazy? Well, remember I said the grasses in the Midwest? Because normally it's fairly dry there, their grass roots went way, way, way deep, and they were really strong roots. Well, what happened? That formed, and remember I said the topsoil was so thick. What they did, the people who came out and settled in those areas, they found out that upper crust of grass roots, basically, it was like sod. If you've ever sodded a yard, the sod comes with about an inch or two thick of soil stuck with the roots there, okay? They just went in, except they did a foot or two, or maybe 6 inches to a foot, and they just dug up bricks of that matted material held by the plant roots, the grass roots. And that's what they used, literally, to build their houses. They used the sod, and they called those houses built out of bricks of sod, soddies, S-O-D-D-I-E-S, okay? Now, they made the bricks very thick, probably 12 to 18 inches thick, and probably almost that deep, maybe 6 to 12 inches deep. And they made bricks out. They just dug them up in the shape of bricks and piled them on top of each other and built their houses with that, leaving an area for a door, an area for a window, and going on. Now, several things about that. Those bricks of sod held together really well, okay? And the roots sort of acted like the cementing agents on them. And they were so thick, they made great insulation. And even though it may have gotten plenty of rain out there, it still was really cold in the wintertime. And that wind came whipping down the plain because no trees were there to block it. Those houses were very well insulated. Now, a lot of those places, over the years, the sod would start being worn away by abrasion, natural sandblasting, deflation, that kind of stuff. So building, if they were wanting to hang on to the old soddy, they would build an exterior wall out of something else, bricks or something else, but keep the basic structure of the house. And then maybe put sheetrock on the inside, frame it up on the inside, but leave that really thick wall. I know that happened because a friend of mine invited me out to her place. They had a ranch out in the sandhills of Nebraska, which were dunes that somehow got there, okay? The sandhills of Nebraska, and her mom lived in a old soddy. You wouldn't tell it by looking at it from the outside because it looked like a regular house there. Inside it had regular sheetrock walls, but you looked at the windowsills and they were that thick, No one built houses that thick. That was where the sod was. Hers was an old soddy and didn't need much insulation because that is really well insulated. Okay. So the whole purpose of that story is they dug up the roots because the topsoil went down in feet, dug up the roots, built their houses, plowed them, did whatever they could, planted their corn, planted their, I don't know if they had soybeans back then, whatever the crops they were trying to plant, trying to get it civilized, you know. And for a few years, they just had wonderful success, wonderful, great crops, okay? But then the weather went back to normal, which they didn't realize this was normal, and it got quite dry again. Well, the wind kept whipping over the plains, but now there was no prairie grass there to protect the soil. There were no prairie grass roots to hold the soil in place. There were fields and furrows, and that wind came whipping through there, and what did that produce? Does anyone know? The great dust storms, the dust bowls. Have you heard of those? I think that was around the 1920s or so. That was because we went through there, us, the settlers went through there, dug up the native materials, started trying to crop it, row crop it and stuff. It went well for a while until the weather changed, went back to being dry, went back to being windy, always was windy, and now they started losing it. And they said that dust from the Midwest, from those dust storms, the Dust Bowl, made their way to Philadelphia and New York and Boston and those areas, and there were lust deposits there from that good old Midwestern soil that we had exposed. Okay? Another example of lust. All right, now, development of landscapes. Okay, you're going to see in a slide or two, you're going to see some very familiar terminology. But let's first look at this. This is, by the way, section 20.5. Now, before we get there, let's back up a little bit. They have a little blurb, myths, mistakes, and misunderstandings. As unchanging as the hills, you may have heard that phrase before, the hills are always a-changing, okay? It's just they take a lot longer to change. So that I thought was a fairly lame little blurb. But the one on page 518, Science and Society, this thing on acid rain, that is pretty impressive in what it's showing. Well worth a read. There's several questions you can ask, discuss, or think about. Here are some of your what they call PHs. This is a way that they measure how acid a soil or a material is. Just about the strongest acid there is hydrochloric acid. It has a pH of 0, which means it ionizes everything. Some of the next most acid conditions are found inside your stomach, okay? Because your stomach is digesting food, it's breaking it down by acid decomposition. So your stomach has acid in it in 1.6 to 1.8 pH. That is really, really acid. If you've ever had really bad nausea, that you're really bringing stuff up, you know how it burns your throat. That's because your esophagus isn't used to that kind of pH. Okay? And people with acid reflux, you know exactly what that is. It's awful. It's also why if someone has ulcers, what that means, you have sort of an infection or something in your stomach lining. Your stomach lining is some of the most incredible material on the planet because it's able to contain that acid inside, not be hurt by it, and not allow it to hurt anything outside of it. Okay, because that is really strong acid. But if you have a weakness, a sore, or something like that in that's what an ulcer is. And now the acid is getting into sensitive material, and that's why the ulcers hurt like crazy. Okay, lemon juice, really, really acidic. Not a good idea to be drinking lemon juice or sucking on lemons. 2.2 to 2.4 pH. It'll actually eat away the enamel of your teeth. Not a good idea to do. Vinegar, 2.4 to 3.4. I really like the taste of vinegar, especially in dressings and things like this. Not doing a good job on my teeth either, probably. Unbelievable. Carbonated soft drinks, remember, carbonic acid, from 2.0 to 4.0. But they're made so sweet and tasty, we don't notice the acidity in them. Okay? That's why there's so much sugar and flavoring in them. Grapefruit, 3.0 to 3.2. Okay? Oranges, 3.2 to 3.6. Acid rain is just about like sprinkling orange juice or carbonated soft drinks on the soil, 4.0 to 5.5. Tomatoes, pretty acid, 4.2 to 4.4. Potatoes getting very neutral there, but still slightly acid, 5.7 to 5.8. Natural rainwater, 5.6 to 6.2. Still slightly acidic, because every time there's lightning, there's a little bit of nitrous oxide and nitrogen oxides that form nitric acid, or an acid of nitrogen. Any sulfur that's in the air forms sulfuric acid, which is another very, very strong acid. So natural rainwater has slightly acidic, but the acid rain, and that's places where you've been polluting with a lot of sulfur material, that's why the pH drops from 5.6 to 6.2 down to 4.0 to 5.5. Milk, which most people drink if they do have ulcers, 6.3 to 6.7, still slightly acidic, but not too bad. Pure water is absolutely neutral, 7.0. 7.0 is absolutely neutral. Anything below 7 is slightly acidic. Now, they didn't list the things above 7. Those would be things like your hydroxides, okay? Those are things like most soaps are maybe up around 8 or something like that. So those are things on the other end of the alkalinity scale, okay? So well worth a read there, okay? There's a thing they're talking about dune angles. I found that one less than really all that attractive, but you can read it if you'd like. The person behind the science, this a little small blurb here, John Wesley Powell, and I don't quite get the understanding of their word here, was the most romantic figure of the 19th century U.S. geology. Well, either U.S. geology didn't have very many romantic figures, or he certainly, there's something else being said there, okay? But it's well worth a shot to read this. He was one of the first to steer away down the Grand Canyon. A lot of really interesting things he did. Usually, and included here are other people: Grover Carl Gilbert, Clarence E. Dutton, W.H. Holmes. There's a bunch of potential paper topics there. If you haven't determined a paper topic yet, start working on getting a paper. Okay. So now we're finally ready to start 20.5. Development of landforms. Now, what do we mean by landforms? Basically, the features, the Earth's surface features. Okay? If we had done a lab today, one of the things we were going to talk about was going to be Red Mountain. That was going to be one of the things we were going to look at. That is a feature of this area. Okay? Double Oak Mountain, Shades Mountain. All these are features of the area. The valleys in between them are features of the area. Those are the landforms. Go over in Georgia. There's Brasstown Bald, I think, is one of the names of the peaks there. Stone Mountain, of course, we've talked about before. There's a feature in Georgia called Little Grand Canyon, which is kind of an oxymoron, Little Grand. But actually, someone did a really dumb thing and started erosion going, and no one's been able to get it to stop. The Grand Canyon was made naturally. This one was not. But there's other things like this. Those are the landforms. Now, some of these are broad features, like I said, mountains, plains, plateaus. There's one plateau that's in eastern Alabama and western Georgia called the Fort Valley Plateau. That's where some of the best peanut growing in the world is done on the Fort Valley Plateau. It just, conditions are just about perfect for growing peanuts there. But then there can be smaller things like minor features, hills, valleys, canyons. Now the Grand Canyon I think would be a broad feature, but most other canyons like Little River Canyon or something like that, I've heard these names before, those are more minor features. Okay? Now, generalizations about these main features, these landforms, are based usually on one of three things. The first is the rock structure that was there originally. And as I've already alluded to several times, if the original rock structure was really hard rock, okay, the other meaning for hard rock, then that's going to leave a certain structure, okay? That's the rock structure. That's going to create certain features. The other then is the weathering and erosion, what has been eating away at that original rock. If it was soft rock, it may have gone under a long time ago. Hard rock may still be hanging in there, but still being eaten away. So the degree of weathering and erosion. Here in the southeast, enormous degrees of weathering and erosion. The Appalachian Mountains are rounded mountains because they've been undergoing erosion for such a long period of time. I've heard it said before that one time in the Earth's formation, the Appalachians were probably the tallest mountains on the planet. But they have not been growing, they have been eroding, they've been worn down, and the others have been building up. Now, weathering and erosion has been occurring everywhere. The stages of erosion are the other part of this. And like I said, Southeast has really intense stages of erosion, whereas places like the Midwest, especially northern Midwest, the erosion may be somewhat retarded by the fact that you have less weathering going on because of the climate there and things like that. Okay, so this is the overall development of landscapes. Now, let's look at each one of those generalizations. First, the rock structure. This determines the shape of the minor landforms. Okay, a lot of this depends on the type of rock that was there. If that was good, old, solid granite, igneous rock, coarse igneous rock, then more than likely that's very resistant to erosion. That is going to help create a landform that's very characteristic of tough, hard, igneous rock. However, if there's metamorphic rock is also incredibly hard because you've had more pressure and stuff. So that may create something. Some of the marble outcroppings and things like this, very resistant, especially to chemical weathering. Okay? However, sedimentary rock, oh my goodness, that's very susceptible to chemical weathering, and I would also say physical and perhaps even biological weathering, or mechanical or biological. But chemical weathering especially, because remember, sedimentary rock is just held together by that cementing agents they're basically chemicals themselves. You get a lot of chemical weathering, breaks those apart, there goes your sedimentation. It's now sediments again, it's no longer sedimentary rock. Now, some rocks have attitude. No, what it means by attitude of the rock is the effect, and this is something where I'm going to wait till this gets out of the way. It's going to fade away in a minute. The effects of disturbances either by faulting or folding. And I was surprised at the things I found today to do on the lab, that it really shows some faulting and folding there. Okay, and we'll see that in the lab we'll do next time. Let me wait till this gets out of the way. The attitude of the rock has an effect on it's the effect of the disturbance by folding and faulting, but the folding and faulting can also hasten erosion. So the attitude of the rock may is caused by the features of that faulting and folding, but the faulting and folding can also create deterioration of the rock by hastening erosion. Okay, tried to get that in while you could see it. So let's move on to weathering and erosion. The weathering and erosion processes, and this is stuff I've been talking about all along. Weathering and erosion are influenced and controlled by such factors as climate and elevation. Climate is made up of moisture and temperature. Those are the big components of climate. How much moisture is there? What kind of temperatures do you see? I've already given you that rule of thumb for every 10 degrees Fahrenheit above 40 degrees Fahrenheit, your chemical weathering doubles every 10 degrees. So when we have 50-degree days in the wintertime, you have doubled the amount of chemical weathering that happened at 40 degrees. When you get up 60, doubled what it was at 50. 70, doubled again. 80, and think about how many days we're above 80 degrees. Above 70 degrees, okay? Above 90 degrees. The chemical weathering just takes off and goes. Warm, moist climates, fantastically ideal for chemical weathering. Chemical weathering dominates then. Okay, the landforms will have softer rounded outlines. Think the Appalachians. Okay, now elevation they're not saying as much about, but elevation will also the greater the elevation and the steepness of elevation, then things like the water erosion, wind erosion will have greater effects on those kind of things. So they sort of left out elevation. Now let's go to dry climates. The dry climates, mechanical weathering or physical weathering dominates there because you have to have moisture to have chemical reactions. You don't have it in dry climates, so mechanical. So the sharper angular outlines are much more common. So the Rocky Mountains, the Sierra Nevada mountains out there, much drier, much more angular. Of course, there are also newer mountains that are just still being formed, but you won't have as much rounding as you have with chemical erosion. Okay, so dry climates, and that's where you have the ventifacts or in the rock outcroppings that you'll see out there. Okay, now the stages of development. Now this is the third thing here, stages of erosion. They're now calling it stages of development. Okay, now I said you've seen this before, here it is again. Describes the cumulative effects of the formative processes. Now we're talking about shaping their surface. The youthful stages of development, same term we use for valleys. Okay, youthful valleys, the weathering and erosion effects are just at their beginning stages. Everything's pretty angular. The mountains have steep peaks, narrow, steep valleys. Just like we talked about before with the valley development, the landform development's the same way. When you have a more mature landscape, your original structures have been worn down. Now your peaks are more rounded, the slopes have decreased, and things just move a little more slowly. Okay, and then where I'm heading, old age. Okay, characterized by nearly flat rolling plains. Yeah, there can be a little bit of topological difference, but it's pretty much just rolling plains. Now, the peneplains, I've seldom seen these words except here, are the nearly flat surfaces. Now, I would tend to say go south in Alabama until you get in what they call the wiregrass region and the areas around there. Yeah, you can see for miles. You don't see many hills. You sure don't see many mountains. But every now and then you'll see something sticking up, a monadnock. Now, what a word, okay? Monadnock. Those are hills of highly resistant rock. That has to be what Stone Mountain is in Georgia. It has to be a monadnock, okay, because it's just sticking up there and it's very resistant, okay. Now, it's not always highly resistant rock. The hill where we built our house in Georgia is a clay hill. My goodness, when they went in with that bulldozer trying to level up the site, they said it almost tore up the bulldozer. That clay was so hard, so resistant to any kind of change. All around there, there's topography. That hill is there because that clay, not rock. Now, there's some rock in there too, but not a whole lot. But it was a highly resistant clay. So it's not just resistant rock, it can be resistant clays as well. Now, rejuvenation. Just as land is being lost, other land is being uplifted. Our whole plate tectonic effect. Whenever things are moving apart, something has to be moving together. Land is uplifted. It could be being uplifted through volcanic activity. We don't have much of that here. In fact, we don't have much uplift here in this part of the country. Okay? Out west, yes. Out in the Pacific, yes. Okay? There's lots of uplift happening. There is still some here, and we'll see that. Most of ours was folded, though, and some faulting. And we'll see that in the lab. All right. Notice those same three terms, youthful, mature, and old age, for stages of development, landscape, also valleys. Use the same terms. And that happens to be the last slide in the set. Okay? Did want to mention just a few things. We were talking just sort of on the side about how glaciers have been retreating when at the time it seems like possibly we should be entering a cooling down effect, but it's not happening. We'll talk about that more in later chapters. But I can think of two more examples besides the one I told about the Columbia ice fields in Canada, how the tongue of the glacier is more than a mile up the hill from where the glacier once was. You can't even see the tongue from where it was when they first discovered it. Europeans first discovered it. You have to walk more than a mile around the bend and then you finally see that. Okay? Here's another example of this. Now, I mentioned this before. Mount Kilimanjaro in Tanzania and Kenya, Africa. Right very close to the equator, but one of the tallest mountains in the world as far as height of the mountain, not elevation of the mountain. Himalayans got it beat long shot, but Himalayans are on an uplifted plateau, so they don't stick that high above the surrounding area. We'll be doing some of that in the lab too. But Mount Kilimanjaro, back when, goodness gracious, I'm going blank on his name, famous writer, wrote The Snows of Kilimanjaro was one of his books. Oh my goodness, he lived about the time of World War I. He actually, I think, fought in World War I. Yeah, why can't I think of his name? Really famous writer. But he wrote the book, The Snows of Kilimanjaro. Now what he was talking about there, and by the way, here's Capri is back. Let me let her back in the room. Okay, there she is. Okay, back, World War I was right around 1915, 1920. That's when World War I happened. Sometime either before that he was there. I'm so close to saying his name and I can't get it out. But anyway, he wrote the book, The Snows of Kilimanjaro. Kilimanjaro had glaciers on it. Even though it sits right on the equator, it was such a tall mountain that it had snow. Year round, it had snow. And that was the name of his book, The Snows of Kilimanjaro. If you go to travel in that part of Africa now, you see a very tall mountain, but no snow. Okay? Between 1920 and 2020, all those snows have gone away. Sadly, but true. There is a national park in the U.S., a beautiful national park called Glacier National Park. It's mostly in the state of Montana, but I think a little bit of it goes into probably Wyoming and Idaho as well. When that national park was put together, and that was probably around 18 something and others, when they made it a national park, I don't know exactly when, but it had glaciers all over it. Now I think they're down to maybe 6 glaciers, maybe 7. Most of the glaciers have melted, and the ones that remain are minor glaciers. They are the remains of major glaciers that were there that got its name, and they are like the minor glaciers that there just happened to be there before. Those are all gone, and you just have a little bit of the glacier. At some time in our future, it may be that Glacier National Park will not have a single glacier in it, and that will be sad. Okay. All right. Now, as I say at the end of every chapter, nothing replaces reading the book. I hope you've already read it. I hope you'll go back and at least read it again or skim it, review it. The summary here is one of the shorter summaries I've seen, and the key terms is one of the shorter lists of key terms I've seen. Applying the concepts, a little bit on the short side there too, 45 questions. That's still a good number, not far off the average. They have the answers provided. That's probably your best shot at studying for your test. Okay? The questions for thought, no answers given for those, but you can find them fairly easily in the text. That's about normal. 18 questions. A few chapters have 19 or more. Some have fewer. For further analysis, 3 may be a little on the light side, but not far off. There's an invitation to inquiry about frost wedging. If you wanted to follow up on that, that's there. The parallel exercises are just whether you want to do those or not. They're more like the examples that may have some interest to you, but there's no answers given there. Okay? So, what does that mean? We're now at 6:05. We're not going to do chapter 21. Now, I'm sort of wishing we might have, or at least included it. We wouldn't do it next. We would go on. And we're not doing chapter 22, which is another really good chapter. That is the atmosphere. Okay? The atmosphere of the Earth, which is a very important topic because it, again, if we didn't have the atmosphere we just happen to have, of the composition it is, the thickness it is, and everything about it, life would not be here as we know it. Okay? So we're moving next into weather and climate. Now that's going to be an interesting chapter for me because it used to be the lab that we did for this chapter was a field trip to the Channel 13 Weather Center, because I know Jerry Tracy, who's the main meteorologist there at Channel 13. We go to the same church. I've known him for years. He's a really nice guy, and he always hosted us or had someone host us when we went. We can't do that anymore because of social distancing and stuff. So I've got to come up with a whole new lab for this chapter. The one I'm using today, I had to come up with parts of it because we couldn't use some of the things. Just like the last lab, I had to come up with parts. So this is going to be, I don't know when I'm going to have time to do it, but I've got to get that done. Okay? I still got to finish the parts of today's lab. I have it written out. I just don't have it typed out. So we'll be starting. We do have time that we could start on weather and climate today. So let's do that. So let's end this slide. Show. And go down to screen sharing is stopped for right now, but hold on for a moment. And I'm going to see, can I get to it from here? I think I can. Here we go. Chapter 23. My wife must be home because I hear the dog outside. Okay. Why can't I get chapter 23 to come up? There we come. Okay. Now let's go back to here, and let me see if I can pull up chapter 23. There it is. Okay. Can y'all see that now? Yay or nay? Yes. Okay, good. All right, so let's start from the current slide. Now, some things from the previous chapter, chapter 22 on the atmosphere, I'll be bringing in where we need them. But here's chapter 23, and that's a fairly familiar sight these days, isn't it? Not over the ocean, but boy, when my wife and I were driving back from, we had gone up to Smith Lake this weekend, and we were driving back from there, we saw clouds almost this ferocious. In fact, we drove through some of that heavy rain in there. I would not want to be on that sailboat right there, because that is about to get dumped with rain and probably some pretty strong winds. That boat's probably going to be doing a lot of rocking, but that one's going to really take it hard. These people need to get off the beach because that's a pretty major looking storm coming. Okay, so in this chapter we're talking about weather and climate, and basically that's how we're going to do it. Approximately the first half of the chapter is going to be on the weather, and the second half on climate. Now, are those the same things? Is weather the same as climate? Climate the same as weather? What's your thought on it? Weather is what's happening right now. The temperature out there, the wind speed right now, the relative humidity right now, amount of rainfall we had last night, this morning, yesterday, whatever. That's weather. That's the more recent stuff, the things that's changing constantly. If you don't like the weather, wait a while. It's going to change. Okay. Well, climate is the big picture. What has been going on over time, over long periods of time. It's talking about the same type of measures, but very different time scales. That's the difference between weather and climate. Okay. Here's the core concept. Solar radiation drives the cycles in the Earth's atmosphere. That was last chapter. We didn't study it, so we'll talk a little bit about that. And some of those cycles determine the weather in the short term, but also the climate in the longer term. Now this picture here, and this isn't the same one that's in your text, but this is a pretty good one. This is a pretty nice shot of the Gulf of Mexico. Okay, here's Florida, there's Cuba, there's Louisiana. Like I said, there's probably the Mississippi coming right down here. Okay, that could be it over there. I can't tell for sure. But there's Louisiana sticking out into the Gulf of Mexico. Why? Because of all the sediment. The deltas that have been formed over the centuries and millennia have built the state of Louisiana. Probably a third of the state of Louisiana is stuff that used to be upstream here. Okay, there's then you go into the coast of Texas, somewhere here Mexico picks up. This may be part of the Yucatan Peninsula. It doesn't seem quite right, but you can look down. This is either a very high atmosphere shot, maybe from a plane or balloon or something like that, or I don't think this is a satellite shot, but you can see the Gulf of Mexico. You can see prevailing winds creating very similar wave structure and stuff like this here. A little bit different on this side. Okay, very different down here, but it sort of gets lost in the clouds down here. You see a lot. A lot of times you can't see this stuff. There's a cloud bank here, a cloud bank here, but you can see almost the land here. Okay, solar radiation drives these cycles. Okay, and some of them determine the weather, and then long term the climate. Okay, where we start, 23.1 starts with clouds and precipitation. Now, if there's one thing hopefully you've gotten out of this class, is that everything moves in cycles. We had the rock cycle, we had the whole concept of uniformitarianism. Here we have the hydrologic cycle. Clouds and precipitation. Here's a good graphic of this. Most of the Earth's surface is covered by ocean. Something like close to 3/4, between 2/3 and 3/4 of the Earth's surface is covered with water. So that's what most of the sun is hitting most of the time, is water. And that sun hitting the water evaporates the water. And the water vapor goes up into the atmosphere. When it gets up there, it tends to cool, because somewhere up there you hit cooler bands of air, and now you get clouds formed. Okay, and that's what we're going to be talking about. The clouds are picked up by the prevailing winds and brought back over land. And usually land in the summertime might be warmer than the water temperature, but in the wintertime, land is usually colder than water temperature. So when it gets over land, then maybe some of this starts dropping out of the clouds. Certainly if the land rises in elevation, you have mountain ranges and stuff like this, definitely you get the rainfall coming out of the clouds. Okay? Well, the rainfall comes out of the clouds and hits the surface of the land. Hopefully most of that rainfall soaks into the land and goes into something we'll talk about next chapter, groundwater. That's where we want it to go, but some of that, sure enough, stays on the surface, washes back down, sometimes eroding the surface as it goes, as we talked about in the last chapter, but ultimately goes back into the ocean. Okay? Now, several things are happening here. This water that evaporates off the ocean is fresh water, pure, pretty close to pure water. That's what makes its way into the clouds. Now, some salt crystals also make their way up here, but most of the salt is left in the ocean. The water is what evaporates. When it hits the land, though, it hits the land and starts dissolving things. Remember, water is a great solvent. Starts dissolving minerals and carrying them back to the ocean. So that's why the ocean water is salty. Usually land water is not. We'll talk about that in the next chapter. Okay? But this is the cycle. Always happening, continually happening. It's called the hydrologic cycle. Hydro means water. Hydrogen oxide, that's what water is. The hydrologic cycle. Evaporation from the ocean, transport through the atmosphere, condensation and precipitation as it rains in, and then returning to the ocean. Now there's many smaller subcycles. Like a lot of rainfall happens right back into the ocean. It doesn't go very far. Okay? You also have bodies of water here on land that evaporate and make new clouds. And especially in the wintertime, snow. Lake effect snow happens in Rochester and Buffalo, New York, and places like that. So you have smaller cycles going on here, but the big hydrologic cycle is this one. Okay? And that's where we begin the chapter, and that's where we'll end for today. So we'll start next time in cloud forming processes on page 575 of my book, 23-3, if you have the smaller condensed book. Any questions, any comments, anything to say? So let's just talk quickly about next time. Next time we'll have from 2:30, and hopefully we'll all be able to be here at 2:30, until 4:15, we will have class. Mostly in, almost totally in chapter 23, I think. I don't think we'll come close to finishing 23 in that time. Okay? Then at 4:15, we'll have the lab from the last chapter. Okay? It's basically going to be talking about topographic maps. If you looked at the lab that I put out there, because I was thinking we might have time in the lab today if Zoom hadn't screwed up, we may have, but that was the main part of the lab, but there's only 10 points for there. Got to come up with 15 more points, and that's what I was doing, having to come up with. Okay, so anyway, there will be that. And then also, once we finish that lab on Monday, I will then post the tests for chapter 20 that we just finished. I could go on and post it now, but I think you might learn some more stuff from the lab that may help you a little bit on the test. Probably not. Do y'all want the test earlier or later? What do you want? Want me to post it between now and Monday or wait until after Monday? Okay. Well, it won't be right now, but maybe later this evening I'll go on and post it. See, I've got to get it into a format I can post because it used to be I just made copies and passed them out. Now I have to reformat it so I can put it on uh, in a Word document. Okay. So yeah. Okay. I don't have those dates in front of me, but it's around, isn't it around the 23rd of July? They have moved up the date a couple of times, so I don't know exactly when it is. The 23rd of July may be the last day of class. I don't remember. Do you remember? Yes, the final exam will be just like the test. I will put it out there. The last day of class, I'll put it out there, and we usually have a week of final exams. We may not have but a few days this time, but it's going to be a very easy test. All these tests have been mostly multiple choice, some fill in the blanks and other things like this. The final exam is going to be matching. So you'll be able to do the final exam probably in 30 to 45 minutes, I'm guessing. So, but you can take a day or two to do it if you want to. But it's going to be one of the easier tests that you have. And I think you'll find it pretty easy to do. All right, good deal. Good question. I'm glad you asked. Any other questions? Okay, sorry we got a late start today. I don't know what happened, but it sure was squirrely. So anyway, we'll stop sharing right now. And unless there's any final thoughts or parting shots, I will end the meeting for all. Anything? Appreciate your being here. You five were probably the only ones that even got the message. So I don't know where everybody else was today. They must be on vacation from the 4th of July. All right, we'll see you then on Monday. Have a good weekend. Bye-bye.